now I did full screen of my presentation, so I do not see any sort of notification here coming from Google Meet. So please let me know if people have any question, interrupt me to ask the question, and then I follow that. Okay?
Actually, we postponed all the questions to the end of the session, so you can continue until the end, and after that, all students will note all the questions and they will ask you.
Okay, that's fine, as you wish. So, Bismillah. Let me start with one of my regrets these days. So since the time that I've scheduled this meeting with the brothers and sisters in Basrah University, I was thinking that, okay, we are close in a region, and now we should basically talk with the language of somebody else in very far region. So I started at least writing my name in sort of Persian or Arabic style that you can see. I know how to write it, Jamaat al-Basra, and this is 27th of Shawwal. So starting with that, let me, after this regret, start with the fun stuff about this distant learning, which all of us experiencing. Before going to that, let me know if you had online classes this past year. Did you have it? If anybody hear me, did you had online classes last year?
Yeah, of course, doctor. For last 2 years, this year I mean, and the last year.
It is 3 semesters that we had it.
Yeah, 3 semesters attending the online classes.
Okay, so when starting this crisis happened, and education went on distance learning, all of us were sort of confused. What is the platform that we should use? All of us had many questions, and then this basically the online classes, this is the style that usually happens, when the professor or the lecturer giving the lecture, considering all the students and participants participating such serious, as you see, this is what basically prof think. And what is in reality is that, and you see all people following the lectures that way. So I'm trying to have this lecture to be interactive. Dr. Kian said, to have it, all the question at the end of the lecture. But as you wish, I'm open. If you have any question during the meeting, you can interrupt me and ask about it. So starting with that.
Can I ask you a question, please?
Yes, brother.
How we can overcome this problem? Like most of students are taking a nap during the lecture. I mean, whatever we do, like with all the attraction we are giving in the lecture, most of students are taking a nap. Yeah. And all of a sudden, like we can discover that most of the time, like at the end of the meeting, when we finish the lecture, we see that most of them still in the lecture, and we already said we are done. So I mean, I wish I can solve this problem. Like I can get an answer for that.
Exactly. This happened to me a lot of times this past year. I guess there are many factors, playing a role in that. But one thing that we should basically mostly focus on that. Maybe we should. This is only my sort of humble opinion about that. So maybe it's better to focus on basically learning instead of, transferring knowledge to the students. Maybe if we focus on basically the deep learning for the students and providing some materials that they cannot find it anywhere else. If basically we have, this is my basically challenges these days as well. And talking with the students, they're basically talking about these issues. Basically, yesterday I received a comment from the students exactly about this stuff that I'm talking about. So if you basically have transferring the knowledge from the textbooks or other materials which are basically students have it in hand, maybe they are less motivated to actively participate in the class. But instead, if we can basically change the method of teaching and education in a way that, let's say, people talking about flipped learning method, and I'm sure you have heard about it. So you have some content and some materials, let's say prepared offline lecture, recorded lecture or so on, prepared offline. You can give it to the students a few days before the class, and in the class have a sort of actively talking, questioning, challenging the topics, the idea people students saw previously in the files that you sent. Maybe that helped. Not sure, but maybe that helped. A few weeks ago, I had a lecture here in Ferdowsi University in the education week we had here, and I was basically talking about the perspective of this environment that educational institute will have in following years, maybe about 5-10 years. I guess we will have a new basically environment in education sector. So we all the lecturers, professors, students should prepare for that perspective. We can talk about it anytime you can. I have some idea, and I would be, it's my pleasure to talk about it as well. To set the ground, I see that you can chat in the chat bar. You can type here. Let me know how many of you are undergrad students. And let me stop sharing because I want to know your answers here. Let me see. So you can, if you want to answer positive to my question, just type 1 and enter. And if you want to answer no, just type 0 and then enter. Then I can count how many of you are undergrad students in this session.
Professor, can I translate it? Because some of our students cannot understand English, you know that.
Absolutely, yeah.
So basically, you're saying if you are undergrad students, just press 1, right?
Yeah, exactly.
طلاب إذا تسمعوني طلابنا الطالب كلكم طلاب البكالوريوس بالتعليقات كتبوا لنا رقم 1. طلاب البكالوريوس كتبوا لنا رقم 1 بالتعليقات، لأن البروفيسور يريد يجي يحسب عدد الموجودين الآن اللي هم طلاب بكالوريوس.
Very good. Quite few students. Very good. Very good. That's very good for such session, to have many sort of undergrad students. That's fine. And also this is tough for me to basically tune the level of the lecture in a way that our undergrad students can understand it. How many masters and PhD students we have in this session?
طلاب اكو بيكم واحد طالب ماجستير او طالب دكتوراه. I don't know if we have announced that for masters and the PhD students.
Or basically grad students, yeah.
Yeah, I'm not sure about that, but okay. We can for sure tell that there are many undergrad students in this session.
Okay. Do we have any lecturer, prof, postdocs in the session too? I guess we have quite few.
Yes.
Of course, all of them.
Ahmed Joe. Alaykum assalam. Alaykum assalam. Yes, there is some lecturers and professor in this meeting. For example, Professor Jassim Al-Asadi, one of them.
Ahsan.
But almost the undergraduate student now.
Okay. Now I sort of understand who are the audience. Then I can continue. But before that, do we have any students who see general relativity before? Okay, if not, then I should sort of have a part of introduction about that. Okay, okay, fairly good. Let me continue with that. Okay, let me share my screen. You see that? Okay. So let me give you a big picture for theoretical physics that we have. Since most of the participants are undergrad students, that would be nice to talk about it. So this is sort of categories that sort of I provided. We have classical mechanics. When you go to university studying physics, you start with this basic material in classical physics. You start with classical mechanics. You learn also classical electrodynamics. You learn about thermodynamics, and also you learn about Newtonian gravity. Newtonian gravity is part of classical gravity, but I put it aside. I put it, separate as a separate topic because I will use it later. Then by mixing the knowledge that this is sort of a chronology about that. When you learn about classical mechanics, also the questions in classical mechanics and in thermodynamics provided the ground for quantum physics. And this is the developing, also scenario in the history of the science, as you see. And also, in order to basically reconcile between the classical mechanics and classical electrodynamics, this is the problem that was more than 100 years ago. Einstein basically suggested a special theory of relativity. And then if you want to mix what you learn from quantum mechanics and special relativity, you will go to quantum field theory. And if you want to have special relativity and also Newtonian gravity included, this is the realm and the region that general relativity works. And after that, basically, this is what physics, suffering from. There is no a framework or a theory that you can embed general relativity into quantum field theory. I will get back to it in a few minutes. But in order to reconcile these two, there are many tries in the physics, the theory side of physics. The string theory that you learn about it, you basically may heard about it. Quantum gravity theories, or in a bigger picture, UV complete theories that they have ultraviolet in the high energy level and limit. They are basically complete, and theory is under control. These are, string theory and all other theories that you may heard, trying to basically have a unique basically description of the theory and the physics. So that is a big picture. What you learn in physics when you go to university, this is the trajectory of that. Maybe the half of it you learn it in your undergrad studies, and after that you go to master's and PhD. If you follow theoretical physics, you will learn this topic as well. There's another way to look into physics too. I call it effective theory concept. Let me give you a simple example. You know the function or the expression 1 plus epsilon x to the power of 6. Okay, this is an expression. And consider this expression is the full theory that we have. Okay, for example, consider that this is general relativity. We also know that you can expand this expression in terms of powers of epsilon. You have the first term, which is 1, which is epsilon to the power of 0. The next term is power 1 of epsilon, then power 2, power 3, and so forth. So this is so far this is exact. You have the expression full theory. You can expand, you can rearrange the theory in another way and get the right hand side. Okay, this is again the equality is here. These two, the left hand side and the right hand side are equal. But now we approximate. We can approximate here. For example, the three first terms here, considering we call it, let's say, effective theory in a regime when epsilon is much less than 1. This is basically an approximate theory, a good approximation of the full theory. Let me show you here. Consider the left-hand side. This is the graph that I have for the full theory, 1 plus epsilon x to the power of 6, to the power of 6. This is the left graph. And the right graph is the graph for the effective theory. For example, consider that this is Newtonian gravity. So Newtonian gravity is approximation of general relativity in a regime of weak gravity, slow-moving object, and so on. And if you want to have corrections to Newtonian gravity, you can consider the following term after those three first terms here. So you can see that between -2 and 2, between -1 and 1, basically the graph in the left-hand side is very, very similar to the graph of the left-hand side. So you can say that in this regime, when I'm in the regime of between x -1 and +1, when I'm here, this is a good, the theory that I have, these three terms here are a good approximation to the left-hand side, to the full theory. As I said, when we have weak gravity system, basically when we are on Earth, in our solar system, when we want to launch a rocket, spaceship, all we need is Newtonian gravity. Maybe we need some corrections to Newtonian gravity, and that's all. That's all we need. So with this effective theory concept, you can basically, instead of going bottom up, you can go up starting from the full theory and then going backward to the effective theory. For example, if you have quantum field theory as your full theory, as a big theory, when you get the limit in which the velocity is much less than speed of light, you recover quantum mechanics. Or when you have large scale in the limit, when you consider largest, so low velocities, large scales, then you get the classical mechanics. So when we talk about full theory, let's say quantum gravity, quantum field theory, or general relativity, all other fields of physics that we're talking are included in that theory. And this is basically the idea of unification in the forces that we know. So in nature, 4 fundamental forces. Strong nuclear force, electromagnetic force, weak nuclear force, and you have gravitational force. And the idea in theoretical physics is that when you go to higher energies, these are combining together, and from when you are in the far left, you will have one full force, which is basically the theory of everything. The theory that string theory, all high energy, physicists trying to basically understand that. And when you basically going to lower energies, gradually, forces, separate themselves from the main branch. So The best description so far, we have those three for strong nuclear force, electromagnetic force, and weak force. This is basically in the framework of quantum field theory, and the theory for that is standard model of particle physics. So when we talk about standard model of particle physics, basically we are in the framework of quantum field theory. And as I showed here, we are in the regime of the energies between 10 to the power of 19 to the 10 to the power of 14 GeV, giga electron volt. And for gravitational force, the best description we have is general relativity. And as I said, physics was not successful to merge, to combine gravity with quantum field theory. This is the problem. All physicists trying to basically find a solution for that. But so far, general relativity, which is the best description we have for gravitational force, is not compatible with what we have in quantum field theory. Okay. Now, when we talk about early universe, when we talk about the dynamics of the universe at early times, we're talking about this region of energies. As you can see, the bottom line is the time lapse of the universe. You see that it is the time between 10 to the minus 43 seconds after Big Bang. And so around that time, this is the time that we have sort of control on the theory, and we can talk about, the dynamics and the physics of the universe. So in this talk, we want to focus in this region. And when you are in this region, so you need two pillars. One is description of matter is given by fields. The classical description of matter by particles break down in that energies. And the other, pillar is gravity, which is the dominant force on large scale. So you have matters, you have different things, you have galaxies, stars, and so on. This described by fields, and the dynamics between these objects is given by the force of gravity. Okay, now we reach to this position to talk about gravity, force of gravity. So first talk about Newton's way of gravity. In Newton's perspective, gravity is action at a distance force. Like the electric force, I'm pretty sure that all of you know about the Coulomb force in electrostatic. So what is the idea in electrostatic? Is basically you have particle 1 with charge Q1, particle 2 with charge Q2. There is action at a distance. They are far apart, they are a distance r apart each other. The force, which of them, feeling, basically exerting on each other, is as the Fe K, which is 1 over 4 pi epsilon Q1, Q2 over R squared. This is basically fairly you understand about it. So in Newton's way of gravity is action at a distance, and then you have particle 1 with mass m1, particle 2 with mass m2. They are at the distance r from each other, and the force of gravity is exactly the same intuition that you have from electrostatic is given by that. Okay. Now, what is the Einstein way of gravity perspective? So in Einstein, way of the perspective for gravity. So the gravity is the geometric property of space-time. First of all, you need to merge the time coordinate in your 3 spatial coordinates to have space-time. So you have an object called space-time. Consider it as a framework, as I'm putting here. So space-time is dynamic. By dynamic, I mean there is a coupling between space-time and matter, as you can see in the right-hand side. The GIF that is here. So this comes from the field theory understanding. Let me back to the electrostatic, understanding. You have charge 1 and charge 2. The field theory way of interaction between these two particles is that you have charge 1, which has a field, an electric field associated with it. Then you have charge 2 with another field, let's say electric field 2 associated with that. Then there is a coupling, there is interaction between these two fields, field 1 and field 2. And the effect of this interaction between the two fields is being fielded by particle 1 and 2 as a force. So basically, force is a consequence of interaction between fields. Okay. Now, when we're talking about space-time being dynamical, meaning that you can see space-time as a field, and you have matter field, and these two have interaction between each other. There is a coupling between these two. As you can see, when object moving, space-time around it, because it's coupled to that, it is being distorted. And basically, gravity is the curvature in space-time because of this coupling. For example, if you consider, the Earth, our planet, if you consider that, and if you want to basically draw space-time around it, because you have a matter field which has energy in that, and there's a coupling between this mass and the space-time around it, there is a coupling between, and there is basically curvature around our planet, Earth. If you want to see it, another picture is that. And then if you want to talk about moving and rotation of objects around another object, we can basically talk about, let's say, consider here that small object over there. Let's say that is moon. We have, and moon is basically being trapped parsec, and parsec is basically astronomical unit of length, which astronomers usually use that. And basically this is the distance between us and the closest star after sun, which is Alpha Centauri, the star. The distance between us and Alpha Centauri, which is the closest star to us after sun, is a parsec. So multiply that distance, that scale, that length, to the 10 to the power of 8. Then this is the realm of cosmology. And you consider the dynamics and properties of the universe in that dynamics. So this picture basically is the timeline of evolution of universe, starting from, let's say, Big Bang, but scientifically there are many questions on that. Basically, what kind of explosion was that? Was it a sort of a unique sort of explosion, a unique event of time, or before that we basically had universe, let's say, contracting phase, and then explosion, and then expanding phase. There are many scientific debates on that, and physicists working on also pre-Big Bang theories as well. So, but let's consider you had Big Bang, and then after that there's inflation, which is basically an exponential expansion of space because of the energy content in that. I talk about it in a few minutes. And then after that, formation of atomic, atoms from nuclei and electrons. You have basically neutral atoms. And when you had neutral atoms, hydrogen, helium, and so on, then the photons, you know, basically existing in that era, scattering from the neutral atoms. This is the Thomson, like the Thomson scattering, and then coming through time to us. And those photons, which are basically scattered at that time, this is basically less than a million, 500,000 years after Big Bang. So you have this you know, fancy blue things, which call it cosmic microwave background, CMB. And after that, the idea is, okay, this matter that you have in the universe starting to collapsing in here and there, forming stars, galaxies, and other structure in the universe. When you want to study basically universe, evolution of universe, you consider phase one, when I basically put it with this box here. So you see box one, and also you see box two after that. When you go back in the when you go basically and observe farther, you know, distances, you basically go back in time in the evolution of universe. So you see both the time one and time two, and then you can examine, you can test your theory. You can see if general relativity, when you have this initial condition at time one, now let evolve the universe with the dynamics given by general relativity, and then you go to the time two. If what you basically simulate is basically consistent with what you observe, then you say, okay, the theory passed the test and theory works. This is basically the typical way which astrophysicists, you know, do science. But there is basically understanding of us. When you consider basically symmetries, you have this Einstein equation, considering the energy is basically distributed homogeneously in the universe in a isotropical way. You got this Friedmann-Lemaitre-Robertson-Walker metric. This is a solution for Einstein equation. So you have this solution for Einstein equation. And from here that I'm talking about, let me show you first here. Now you can do this study until when? Until the time that you receive light. The first light in the universe we receive are from CMB. 500,000 years after Big Bang. This is the first light that you receive. Okay, then if you want to study early universe, you cannot follow basically the method that I told you. You see time one, how universe look like, you evolve it with, let's say, Einstein field equation. If you get the time two which you observe, then Einstein theory works. But when we talk about, you know, early universe, we do not see anything from that. You only see cosmic microwave background, which is sometime after Big Bang, 500,000 years after Big Bang. Now, how we do theoretical physics in early universe? What is the method that we do? So you basically, you know, this is comes to play the effective theory picture that I told you. So you have quantum field theory, which works in high energy physics, and you know, in that region of time, the universe was so energetic. So you apply the rules of quantum field theory as basically you describe matter with that. This is a model building way of basically doing science. And the dynamics between matter is given by Einstein equation. So you basically assume, you consider a initial phase This is you don't have any access scientifically with experience with light to that. You don't see that. So you assume an initial condition. You also assume a theoretical framework, which is basically general relativity plus quantum field theory or classical field theory, and you let them evolve. And if you, with that initial condition that you get, and with the theory, if you are able to produce CMB, what you observe in the CMB, you say, okay, my theory works with this initial condition and with this framework that I'm talking. So one way is you basically see this yellow, blue, and green, and basically orange, dots that you see here are cosmic microwave background. This is CMB. One way of doing science is you start with CMB, you see that, you have that lights. And then you evolve through time to present time and try to see basically what is the evolution of the universe. And then you have another way. You start from another initial condition and try evolve your theory and your simulation to basically be matched with the CMB. Okay? So this is basically a theoretical framework this is an old sky map of CMB. When I look here into the sky, when I look here down there, or other parts in all 4 pi degrees in all sky, you see this is the cosmic microwave background, and this is not the original the light which is in the microwave bound in the microwave region of frequencies. This is perturbations, this is fluctuations around CMB. You have old sky receiving the light from this side and this side of the sky, having same thermodynamical properties, have same temperature and so on. And when you study the fluctuations around that temperature, this is the temperature map. This is the fluctuation of temperature. The blue regions are a bit smaller, have a bit smaller temperature, and the red dots have a bit higher temperature. So this is a fluctuation map. And since 1992, we start observing this with sending COBE satellite, WMAP satellite, and Planck satellite through space. We basically observe and receive this information from our sky, and it's very fruitful materials to study cosmology. Okay, so now we have basically the laboratory for cosmology. The main paradigm, the main laboratory for cosmology is CMB. This is light from the old universe. And we starting, as I told you, we start from an initial condition. We have a theory and try to match this initial condition with this theory to CMB. So the main paradigm of early universe is inflation. And inflation is an exponential expansion of space. Very quickly, space expanded. This description, solved many problems that the standard cosmology was suffering from many years. Maybe at some point later we can talk about it. This purple box here, which I call it reheating, is basically at the end of inflation, you need a mechanism to transfer energy that is in the inflaton field to the other, particles and fields in the universe. So this is reheating process, which was my basically PhD project, which my PhD thesis was on that. Study evolution of the universe in the reheating era when I was at McGill in Canada. So why inflation is the standard paradigm of early universe? Because people talked about inflation maybe 30 years ago. Inflation had some prediction, and one of the prediction is basically this slide that you see it here. Basically, this is the correlation. You see this map. You see this map. If I take, you know, a place in the let's say in the right-hand side, and then if I want to see how similar is the properties of this region to the properties of a region in the left-hand side, the correlation, the similarness of these two is basically given in this map here. As you can see, the green curve is the prediction of inflation, and those dots with tiny error bars on that. This is the data, which we got it from observation from the CMB. So because of that, inflation is basically the main paradigm of early universe. Now the idea of evolution is as following. I'm trying to wrap up this talk in a few minutes. So bear with me, I will finish soon. So you start with fluctuations, you start with perturbations. As you can see, it's evolved, it forms the cosmic microwave background. This is the map of those those fluctuations. And those fluctuations in matter will form the cosmic structures for you. As an example, consider these boxes that I put it here. The first one in the left, in the up left side, you see that. Consider this is the room that we are sitting in, and you filled it with a gas. You have a gas, you know, pumping in this room. As you can see, it's almost homogeneously distributed in this room, but there are some regions with over densities and some regions with less basically densities. Okay, so that you have some perturbations in this distribution. As time evolves, what is the role of gravity? Gravity basically plumb and gravitates basically. The region you have more matter, basically absorb more matter in that region. As time, you know, goes, you will finally go to the bottom right-hand side, the box. All the matter basically clumped in some regions. This is a simulation. This is basically of the universe. You see that. So you had initially you had universe filled with the matter with some perturbations, and then when you evolve the universe, it basically formed for you galaxies, stars, and so on. So these are we talked about this fluctuation in the CMB. What are the origin of those fluctuations? The idea is that basically you had quantum fields in early times. Those quantum fields they had fluctuation in the ground state of those fields. And you have basically, so you had Einstein theory of relativity, the gravity, fluctuations basically in early times expanded and basically provide the cosmic, you know, perturbations for you. And by gravity, this perturbation provided the basically structures for you. And then from the properties in the transformation, when you can categorize, you know, perturbations in different, you know, categories based on the transformations. So you have scalar fluctuations, you have vector fluctuations, and you have tensor fluctuation. And maybe in recent years you have heard about gravitational waves. Basically, gravitational waves are this tensor perturbation. So you basically perturb Einstein equation. The tensor part of that is gravitational waves that we talked about. Scalar perturbations are perturbations in energy density, which I showed you in CM. So, and this evolution of perturbation and in different, times, in inflation, in reheating, after that is basically topics that people basically talk about it. Let me finish my talk with a conclusion. Let me pass. These are different, projects that I worked on. So the conclusion of this talk is our universe is about 14 billion years old. Okay, so this is our age of universe. So probably inflation happened in early times. Why I'm saying probably? Because we're not 100% sure about it. As I told you, you assume initial condition and you assume a theory. If this initial condition is correct, if your theory is correct, then you get to this what you observe. Maybe your initial condition is not correct, your theory is not correct, and this too gives you what you see a compatible signature with what you observe. But so this is not so probable from in a wrong initial condition, a wrong theory, you get a correct sort of theory. So we have some understanding of what's going on. The amplification of quantum fluctuation during inflation in early times is basically the most plausible scenario to basically see cosmological fluctuations. And then when you have perturbations, cosmological perturbations, gravitational instability, the picture that I showed you from different box, from left-hand side to right to this bottom right-hand side, this is gravitational instability, basically forming the structure by gravity. So gravitational instability is responsible for structure formation in the universe. The dynamics between different components in the universe is given by general relativity. Some part that I didn't talk about in inflation, after inflation, you need reheating to happen. The first stage of reheating is a very fast, particle production, which called preheating, and so on. These are different phases of universe that one can study and work on that. So I'm finished with the presentation. If you have any question, I would be happy to answer.
Doctor, can I ask?
Yes, you can.
What's the main point of the distance between the spherical and general relativity?
Okay, so if I understand your question correctly, you said that what is the main point in general relativity? Is
Yes.
that correct?
Yes.
Okay, so as I told you, in general relativity, the most important part is that, in Newtonian understanding, when you talk about coordinate, when you talk about space is not dynamical. Space is, a featureless object. Okay, but the difference is that in the perspective that Einstein has, space-time itself is dynamical. So you have a dynamic with it. You can basically, in my previous works, I had 2 works on trying to basically calculate the energy of space-time. There are different, methods to calculate energy of space-time. So when you talk about coupling, every component in the universe, which basically have energy, they can couple to each other based on general Einstein field equation. Okay. Now, if you have space-time itself has energy, then it can couple to other, you have matter, stars, you have our planet Earth, or anything else. Any math in the universe can couple to space-time, depending on the mass, this coupling might be strong or weak. Any other question? If there is any other question, it's my pleasure to answer.
So, Professor, can we get a record for this lecture?
You mean the presentation that the PowerPoint provided?
Of course, the PowerPoint will be nice, but also the record for the entire lecture. I think somebody is recording now, right?
Yeah,
or somebody from here.
Maybe Mr. Kian is recording.
Oh, that's fine. So we can get it basically.
Yeah, because I see the recording, button there. So somebody has recorded this lecture.
Yeah, I hope this will be published because it's very nice lecture. We thank you a lot for that.
Thank you very much. It's so nice of you. Maybe in near future we can physically meet each other, either in Mashhad here or in Basrah.
It's our pleasure to meet you, Professor.
Yeah, bi'idhnillah. I'm very, that would be very nice to physically meet, your students and your faculty members. It's one of, the desired, thing that I would be very happy to see that. Mr. Abdul Sattar, you have a question?
Thank you very much, Professor. I haven't questions. Thank you for this lectures. It's a nice lectures, and I believe these lectures have very expensive ideas in physics, and all the student and professor, of course, see something is benefit in these lectures. And I hope to continue with our university and our college, Department of Physics and Mathematics, to see good professors in other university like Professor Hossein. Thank you very much for this presentations.
Thank you very much, Mr. Abdul Sattar. It's very kind of you, so nice of you. I agree absolutely with you. That's a very, very valuable, connection that we have. This happened, coronavirus happened, everything went online. Many, crises and, tough times, happened for all of us. But this is the good part of that. This is, you showed us, okay, we can simply get connected through this media, and maybe we can sort of collaborate, maybe students can see something, and we can continue scientific collaboration on that. And this is basically making the Ummah more strong, inshallah.
Inshallah.
Thank you very much. If there is no other question, I need to prepare for another class in a few minutes. So I will say salam to you and goodbye. So ma salama.
Bye, ma salama. Thank you very much.